And welcome, everyone. I'm pleased to introduce today's speaker, Dr. Yannick Pings. Yannick is an assistant researcher here in the ESS department at UCI. He received a PhD in physics of climate at the University of Toulouse in 2010, and then he was a postdoctoral researcher at the French National Meteorological Research Center in Toulouse. He came to Irvine in 2013 as an associate project scientist and was promoted to assistant researcher in 2011. Yannick studies climate variability at seasonal to decadal scales. And today he's going to be presenting his research on regime shifts in seasonal California rainfall. So Yannick, please go ahead when you're ready to get started.
Thank you very much, Alex, for the introduction, and thank you everybody for joining for this seminar. So today I'm going to talk about a new project we have in Magnus Nautilus Group, funded by the Department of Water Resources of California. And that's a project we have started last September. So it includes myself, Gudrun, Yuna Lim, who is a postdoc who joined us in January. And also we collaborate with Eric Sudders and Gabe Hope from the Department of Computer Science. So a quick outline of the presentation. I will briefly introduce the scientific questions and motivation for the project. Then in the results section, I split the results in two parts. Part one is about sensitivity experiments with the atmospheric model WACAM. Part two is results from analysis of the North America multi-model ensemble and NMME. And I will finish by a conclusion and prospect. So let's jump into the scientific question and the motivation for this project. As you all know, California relies strongly on precipitation in fall and winter. And it's really important to store that water for the next spring and summer to make sure there is enough water resources for the state. So here I show a map of the current reservoir conditions across the state. So we see there are several reservoirs spread out across California. That's the conditions as of yesterday. We are actually right now at pretty good conditions in terms of water storage. Most of the reservoirs are close to their climatological average. But I just show this to highlight that in California, water management is crucial, and the decision makers, like the Department of Water Resources of California, are really interested in seasonal forecast to be able to make the right decision and to predict the amount of water that the state will need across the year. So what is the water year? On the top plot, I show an annual cycle of daily precipitation. I'm using here the CPC Climate Prediction Center precipitation data. It's at a quarter degree over the entire US. It's using interpolating institute data. So in black, this is an example for the year 2018 of the annual cycle of daily precipitation in average over California. And in red, that's the climatological average for the 1961-2020 period. So that's a solid line. And the envelope shows the 10th and 19th percentile of the daily California precipitation. So on that plot, we see that most of the rain falls over California from October to April, roughly. As we experienced yesterday, there is also rain falling during other months, especially in May. But usually we define a water year as a period going from October to April. So that's the definition I will use in that presentation. On the bottom plot, I show a coefficient of variation of rain from one year to the other. So it's simply showing the interannual variability in precipitation across the United States. We see that, for example, over the eastern part of the US, there is little internal variability in precipitation. So it's less critical to be able to predict the rain months in advance. But in the Southwest US, there is a high internal variability. So it means the amount of rainfall that will happen is going to vary a lot from year to year. And that's especially the case for California. And that's a challenge, a big challenge for water management and for people who are in charge of making decisions for water storage, water restrictions, and all kinds of water management. So on that figure, I show an example of water year for the year 1983. That's on the horizontal axis, that's time. So we are going from the beginning of the water year, October 1st, to the end of the water year, end of April. It's in millimeter per day, and that's a cumulative rainfall over California. It shows the accumulation of rain across the season over California. The colored line shows the year 1983 with different colors depending on the conditions of the water year. So it's dark blue if it's very wet, blue if it's wet, and then we have normal, dry, very dry. And then in purple, this is the dashed line shows the 1961-2020 climatological average of that cumulative rainfall. And the spread in shading shows the minimum and maximum over that period. So we see here that 1993 was the wettest year in record at the end of the water year, at least. And that was associated with a strong El Niño in the tropical Pacific. So typically, when there is a strong El Niño in the tropical Pacific, we expect to get more rain over California due to El Niño teleconnections that spread over the extratropics and have influences across the globe. Here, the next figure, I show another example of a wet year. That's 1998. Again, strong El Niño year. So El Niño historically has been the main source of predictability used for seasonal forecasting of California rainfall. But actually, that connection does not always work and is intermittent, and especially it has weakened in the recent decades. So 2016 is a good example of that. There was a strong El Niño in the tropical Pacific, but the water year did not live up to expectations. So we only received an average amount of rainfall, while we were expecting an excess amount of rainfall that would have brought relief for the drought that California experienced from 2011 to 2017. And actually, the rain came the year after. So the following year, there was no El Niño in the tropical Pacific, but that's when we had a lot of rain over the state. And that was the beginning of the end for the big drought, the big 2011-2017 drought. So it clearly highlights that El Niño is not enough for seasonal forecasting. That's a driver, but it's the teleconnection, especially in recent decades, has not been as strong as we could expect. So there is a need to identify other drivers of California rainfall at seasonal timescales. Most of California rainfall comes from atmospheric rivers. So I show here an animation of one atmospheric river hitting the western US. Atmospheric rivers are those filaments of moist tropical air that propagate from the tropics to the mid-latitudes and bring a lot of rain when they hit the continent, and especially over the western west coastline. So they carry a lot of water vapor. And there has been a lot of progress in understanding atmospheric river and processes associated with them. So that's the schematic at the bottom. There are different modes of climate variability to who are associated with atmospheric rivers. One of them is the Madden-Julian oscillation, that is intraseasonal oscillation in the tropics that represents an eastward propagation of convection anomalies in the Indo-Pacific tropical region with a periodicity of around 30 to 60 days. So atmospheric MJO is a good source of predictability for the climate in the tropics, but also in the extratropics at intraseasonal timescale. So when we are trying to predict atmospheric rivers, it depends at which timescale we are looking at. So on that plot, I show the 3 timescales of interest for predicting atmospheric rivers, the weather forecast timescales up to 2 weeks, and that one is, of course, pretty good. The skill, I mean, is good. Then we have the subseasonal timescale, and that's the one in which we use MJO especially, but also some other sources of predictability. And there has been some good progress in at this time scale to predict atmospheric rivers and rainfall that are associated with it. But at seasonal time scale, on the right, we rely primarily on sea surface temperature and ENSO. And like I've shown before, that is an intermittent teleconnection, and there is really a need to identify some other potential drivers of seasonal variability. On that plot, I show that there is a good skill in predicting atmospheric rivers up to 3 weeks. So on the horizontal axis, we have the time from week 1 to week 3. To week 5, sorry. And the vertical axis shows the skill in predicting the occurrence of atmospheric rivers over the North Pacific Western US region. So of course, at week 1, we have a very high skill at the weather forecast. Week 2, it's pretty high. And up to week 3, there is a pretty good skill. So there has been good progress at intra-seasonal timescale to predict atmospheric rivers. The problem beyond 3 weeks, there is really no skill. And that's illustrated on that plot. So that's a skill of seasonal forecast for precipitation, averaged from December to February, over 1995 to 2016. So those forecasts are made in mid-November, and they are trying to predict the December to February average of precipitation. And that's for the seasonal forecast model of NCEP, CFSV2. So we see there are some areas in the US that have good skill at seasonal timescales for precipitation, especially in the southern part and southeastern part of the US. But over our region of interest, California, the skill of seasonal forecast model is still very low and not better than climatology. So this is a big challenge for water management, and they are really interested in the Department of Water Resources in seasonal forecast more than into intra-seasonal forecast, because to make decisions for water storage, water restriction, things like that, they need to know months in advance. They need to have the knowledge of what the water year is going to be like months in advance. So they have especially 2 targets of interest. In early October, they want to know how much rainfall we get from October to December. And then they reassess in January. And then they'd like to know what we can expect for the rest of the water year. So intra-seasonal timescales, although it's very interesting, of course, for them, it's not so critical, and they really want to see improvement in seasonal forecasting. In our project, they ask us to focus specifically on a regime shift in California seasonal rainfall. So let me explain what are those regime shifts here. There are simply years that have a transition in the precipitation regime. So for example, the water here is gonna start very dry. We get no rain. And then suddenly we receive a lot of rain. That marks a transition in the hydrological condition over the state. So those years are particularly challenging for water management because you can make decisions based on the water you have, let's say in early January. But if you get a lot of rain in February or March, then the decisions you have made are not relevant anymore. So they like they'd like us to explore if we can gain predictability in those regime shift years. So on that plot, that's an example of a late bailout year. So meaning it was very dry at the beginning in 91, and then there was a lot of rain towards the end of the season. That's a well-known March miracle of 91. But there are some other years with a late bailout that we are trying to understand. That's at the bottom here, the list of those years. And then other years of interest for that project are the opposite, years that are pretty wet at the beginning of the water year, and then they remain dry. We don't get any rainfall for the rest of the season. So an example is 2015. In January, the state of the cumulative rainfall was normal. We had received a fair amount of precipitation, but then there was almost no rain hitting the state in the rest of the water area. And again, on the bottom, that's a list of other early strong shelf years that we are studying. So the questions we are asking and the project goals are the following. Like I've said, seasonal forecast of California rainfall is still pretty challenging for seasonal forecast schemes. And especially the teleconnection with ENSO, El Niño Southern Oscillation, has weakened. So are there other drivers that may increase predictability of water year rainfall? That's what we are trying to explore. And especially we focus on regime shift years. So those years that have a transition in the precipitation regime. And we want to find out if there are some drivers, processes that could explain them. So to be clear, we are not doing seasonal forecasting with that project. We are only investigating processes and physical mechanisms with the hope that by better understanding processes that will benefit to seasonal forecasting on the long term. So let's go with part one of results, sensitivity experiments with the WACCAM atmospheric model. So WACCAM is a whole community climate atmospheric model from NCAR. It's a high-top atmospheric model, meaning it has a well-resolved stratosphere. It has a pretty high vertical resolution, 60 vertical levels, up to 140 kilometers. We use a 2-degree resolution version, which is pretty coarse to study California precipitation because California is a small domain and there are not a lot of grid points at that resolution covering the domain. So I will explain it further later, but we do not focus that much on California precipitation as such. We focus on the large-scale signals that are associated with California precipitation. But by having a coarser resolution, that allows us to run larger ensemble of experiments. And that's what we are really interested in, to try to limit the influence of internal variability in our results. So we've run 3 types of AMIP experiments over 1979 to 2016. So the first one is a regular AMIP simulation with prescribed observed SST&CIs globally. Then we have AMIP with prescribed tropical variability. It's called AMIP trop. And AMIP with prescribed high latitude variability, AMIP HM. So let me explain what those simulations are. So the first type of simulation is the typical AMIP runs that are used in a CMIP exercise, for example. So the AMIP simulation, they consist of running the atmospheric model with prescribed SST and CIs from observations. So in those simulations, there is no interactive ocean. We only force the atmospheric model with observed SST and CIs. So there is no feedback of the ocean in those simulations. And we prescribe the chronology of SST and CIs that we take from ADIST in that case. So we start in 1979, we go up all the way to 2016. And so the chronology of SST CIs over that period is prescribed to the model. And we don't run only one simulation, we run an ensemble of simulation, so 10 simulations that only differ by their initial condition. We slightly perturb the temperature field in the initial state of this simulation. So we get 10 different realizations of the same experiment with only different initial conditions. So the different simulations diverge and we get an ensemble. Then when we average this ensemble of simulations, we isolate the response to the forcing, in that case, at the prescribed SST and CIs. And then we limit the effect of internal variability. So those runs reveals how much California rainfall variability is driven by global SST and CIs, considering that we extract the force signal from the noise with 10 ensemble members. And yeah, that may be a little low, but we get, I think, a good idea of that forced response. And to be clear, they cannot be used for seasonal forecasting, of course, because we prescribe observed SST and CIs that were observed during the water year we are studying. So they give us a predictive skill in California rainfall that we would get if we could perfectly predict SST and CIs months in advance. But they are really useful to explore processes associated with SST and CIs variability. So that plot shows a protocol just to show that it's working. So in black, so those are time series of global SST anomalies. In black, this is for observation, ADIST data from 1979 to 2016. In red, that is for AMIP, so we follow closely the observation. That's what we want, that's by design. And then we have a control run that is called CSST, in which we prescribe climatological SST and CIs. So we repeat the same climatological annual cycle of SST and CIs. So there is no SST internal variability. That's why the curve is flat. So that's a control simulation that we can compare to assess the effect of prescribing observed SST CIs. So now if we look at how do we represent California rainfall variability in those runs, we get this plot. So here I show time series of California rainfall averaged over the water year, the entire water year from October to April. So again, in black, that's for observation, in blue, that's the control, in red, that's AMIP, and I show the envelopes because we have 10 members for the simulation, so we can show the spread. So it's a ±1 standard deviation across the 10 ensemble members. So within the control, it's not surprising, we don't get any scale in representing California rainfall when we have climatological SST. But when we prescribe observed SST, we get a correlation of approximately 0.5. So there is around 25% of variance of California rainfall explained by observed SST CIs variability. The problem, if we look closely at the graph, actually the scale comes from 2 years, especially. The year 1983 and 1988, those 2 peaks here. And if I remove those 2 years from the correlation, it drops to 0.17. So basically, the scale here is only coming from the strong El Niño years. And it's interesting to see that in 2016, the model, when forced with SST and CIs, represent or simulate an excess of rainfall that did not happen in observation. So again, it suggests that this the rainfall anomaly in 2016 was not driven by ENSO, and there were other processes that may explain why we didn't get the rain we were expecting from El Nino. So we get, during those El Nino years, 83 and 98, we get a good representation of California rainfall because we get the right large-scale circulation associated with El Nino. That's what I show on that plot. On the left, this is the 500 anomaly, so geopotential height at 500 hectopascal in NCEP, in average over October to April. That's for 1983. In the middle, we have the anomalies in the control run. So we have no signal because we don't prescribe any SST variability in that case. But when we prescribe the observed SST, and during that year, the strong El Nino, we get the right wave train. So we see that alternation between ridging and trough anomalies in the North Pacific that is typical of El Nino teleconnection. And on the right, I show the distribution of rainfall in the simulations versus precipitation. So the blue dashed line shows the precipitation anomaly. It was approximately +2 standard deviation in 1983. So in climatological SST experiment, the control run, we don't represent any precipitation anomaly, but we get the right precipitation anomaly in our IMIP ensemble. And if I was showing 1998, that's pretty much the same result. However, in 2016, that's a different story. So like I said, there was a strong El Nino, but we didn't get the rain. And the large-scale circulation looked like that. So in NCEP, we see there was a trough over the North Pacific, but there was also some ridging anomalies over the US that prevented atmospheric rivers and rain to reach the western US coastline. And in AMIP, actually, we don't quite get this. We get the trough that extends too much over the continent. So that explains why in AMIP in 2016, we simulate an excess of rain. That's shown on the distribution here in AMIP. So this red diamond, is the ensemble mean of the distribution. And this box plot representation shows the distribution. So the horizontal thick black line is the median of the distribution. Then we have the upper and lower quartile and the max and mean of the distribution. Sorry for not explaining that on the previous slide. So we see that California rainfall is really tied with the large-scale circulation. So instead of focusing on California rainfall index, in those simulations, like I said, we have a pretty coarse resolution. So we focus on the large-scale signal that is associated with California rainfall. So here I show a correlation between California precipitation index, October, April average still, and Z500 from NCEP over the same season. So in contour, that is a regression, and in shading, we have the correlation. So what it says is that when we have an excess of rain over California, we have a trough in the eastern North Pacific and over the western US. So if I compute the correlation between a Z500 index average over this domain, this red domain, we call Eastern North Pacific domain, and the precipitation index, there is a correlation of minus 0.85. So that's pretty high correlation, and this Z500 ENP domain is a good proxy for California rainfall. So in the following, I focus on that Z500 index. Here, I show the time series, like I've shown before for precipitation, but here it's for the Z500 in the ENP domain. So we see that there is a pretty high correlation in the AMIP runs compared to observation of 0.69. Again, it's due to those strong El Nino years, 83, 98, also 2010. But we see that we are still missing some of the years, and especially 2016. In observation, there were ridging conditions that the model does not capture, and it captures trough conditions, like I've shown before. So in order to explore if there are some other tropical sources of predictability, we that could be useful for California rainfall and the large-scale circulation associated with it. We've run another type of AMIP simulations called AMIP-TROP. So they are similar to the previous AMIP simulations. So we still prescribe SST and CIS to the model, but this time we constrain the atmosphere in the tropics between 20 south and 20 north and up to 150 hectopascal across all longitudes. We nudge different atmospheric parameters, so T, temperature, U, V, horizontal winds, and surface pressure. We nudge them so that they follow the chronology, the variability observed in MERA2 reanalysis. So what we do, we take the climatology, the 3-hourly climatology of the model from the AMIP run, and on top of that, we superimpose anomalies, 3-hourly anomalies from MERA2 using a nudging protocol that is described by this equation with a coefficient K that controls the strength of the nudging. So it's relaxing the model at every time step, so it matches the variability from MERA2. So we are basically prescribing observations in the model, but by keeping the model mean state so we don't have inconsistencies. And the coefficient of nudging we use is corresponds to a 5-hour relaxation time scale. So there is still a little bit of freedom. So we avoid unrealistic steps in the model, but we strongly constrain it so it follows the observed variability in the tropics. So this simulation reveals the role of the tropics in driving extratropical variability, including California rainfall. What we do when we prescribe tropical variability like this, we basically prescribe the MJO. So the model does not, this model does not represent the MJO. So by nudging the tropics, we prescribe the MJO in the model. So on the top, I show an animation of MJO anomalies from NCEP, shown from zonal wind at 850 hectopascal. We see the 8 phases of the MJO, and we see the period, this is around 45 days. And as you can see, there is an eastward propagation of those anomalies, depicting the eastward propagation of the convection anomalies across the Indo-Pacific region. On the bottom, I show power spectrum of U200 in that domain. In the AMIP run, on the left, we see there is no peak, no energy in the MJO time window, so between roughly 30 and 60 days. But in AMIP-TROP, we get that peak. So it shows that we are really prescribing the MJO in our simulation. Another plot to show that the nudging protocol is working as it should. I show here the anomalies of the stream function at 200 hectopascal. The stream function is the integral of the flow velocity. So it's a rotational component of the flow. When it's positive, the flow is anticyclonic in the northern hemisphere. When it's negative, it's cyclonic, and that's the opposite in the southern hemisphere. So I show anomalies of the stream function at 200 hectopascal for October to April average in 2015. On the top left, that's in MERA2. So that's a target we've used to constrain the model. On the bottom left, this is for AMIP-TROP. So we see they really match. They are really identical. And here I show the spatial pattern correlation between the two. So we efficiently constrain the model so it follows tropical variability, which is not the case in AMIP. As you can see, if you only prescribe SST to the model, you will get some of the pattern, but not everything, of course. What's interesting is that by prescribing the tropics, we get a good representation of the North Pacific circulation. So that's the same plot as before, but over the North Pacific. And we see that there was this ridging anomaly in observations that is not captured in AMIP, or is way too weak. And in AMIP-TROP, we efficiently represent the spatial pattern of SF200. So we really represent the large-scale circulation in the extratropics by prescribing the tropical variability. And that's something that is true for every year. So here I show a time series of the pattern correlation between the SF200 field in the North Pacific, in MERA2, and in the simulation. So the correlation between MERA2 and the simulation, the domain I've shown before. And then we see that in AMIP trop, we always have a higher correlation than in AMIP, meaning we better represent the North Pacific circulation than in AMIP. So to illustrate this further, here I show the time series of Z500 in the ENP domain, so that Z500 signal that is strongly associated with precipitation. And we see that going from AMIP to AMIP trop, we increase the correlation from 0.69 to 0.83. So roughly we go from 50% of explained variance to 70% of explained variance for that index in AMIP trop. So that's a pretty good improvement. And what's interesting, if we look at 2016, now we are in much better agreement with observations in AMIP trop. So we don't get these trough anomalies anymore. We get more of a neutral or weak ridge anomalies. To investigate the regime shift here that are particularly interesting for that project, I computed a regime shift index that is simply the difference between Z500 in the ENP domain in winter, JFM, minus fall, October, November, December. So if that index is close to 0, it means there is no shift in the trough ridging regime, because you have basically the same trough or ridge anomalies at the beginning and at the end of the water year. But when this index is negative, strongly negative or strongly positive, it means there was a regime shift in the trough ridge regime. So if it's negative, it means there is a ridge becoming a trough, and if it's positive, a trough becoming a ridge in the ENP domain. So that's a measure of if a year is a regime shift year or not. And what's interesting, if we plot the time series of that index compared to observations, we find that in AMIP, correlation is very low. AMIP doesn't capture those regime shift years. But in AMIP trop, we get pretty good correlation of 0.5. So we can explain roughly 25% of the variance in the regime shift index, which is not too bad. And that shows that really there is potential in tropical sources of predictability, not only for seasonal California rainfall, but also to predict a shift or to predict regime shift years. But that's, of course, assuming that you will have a good knowledge and a good prediction of the tropics. And that's a long shot, of course. But here we are trying to see which processes could be important to improve predictability in the mid-latitudes. So then, briefly, we have another simulation called AMIP HL for AMIP high latitude, in which we try to constrain the atmospheric variability in the Arctic. So north of 65 degrees north and up to 300 hectopascal, using the same nudging method as before. And the motivation for this is that there were some, as you know, some big changes in the Arctic in recent decades, dramatic changes with sea ice loss and strong warming in the Arctic. And so we wondered if that may have played a role in California rainfall variability, and especially play a role on the 2011-2017 drought, the very long drought California experienced. So here I show a time series of Z500 in the Arctic. So it's really a measure of the Arctic warming, because when the Arctic is warming, the lower troposphere is warming, you get a rise in the geopotential height at 500 hectopascal. And that's what we see in the observed time series in black. We see starting at the end of the 80s, we have a rise in the height that represents a warming of the Arctic. So that's what we call the Arctic amplification signal. So strong warming in the Arctic since the end of the 80s. What's interesting, if we look at the AMIP simulation in blue, if we prescribe SST-CIS, so here we prescribe CIS loss in the Arctic, it's not enough to represent this Arctic amplification trend. You see that the blue line has a trend, but it's not as strong. So that highlights the fact that CIS loss is only one component of Arctic amplification, and there are some other components, and especially moisture advection from the mid-latitudes. So in the AMIP HR simulation, when we nudge the Arctic variability, that's a green curve, by design, we match observations very well. So what we do in that simulation, basically, is we prescribe Arctic amplification. What we found is that it doesn't play a role on California rainfall variability. On the top, I show the time series of Z500 in the ENP domain. So for AMIP, we had this correlation of 0.69 with observation, basically the same in AMIP HL. So it doesn't change the scale in predicting that index. And that's the same for the regime shift index at the bottom. So that the time series of the regime shift index, we go from 0.16 correlation in AMIP to 0.25. So it seems that at least in our model, Arctic amplification did not play a role in California rainfall variability. Of course, that's for one model, and this kind of studies could be replicated with other models, and maybe we would find a different result. So quickly, I will present the second part of the results. So that's mostly Yuna's work, and she's working on the North America Multimodal Ensemble, NMME. That is an experimental multimodal seasonal forecasting system that groups seasonal forecast model from the US, from NOAA, JFDL, NCAR, NASA, and also from Canada. So they provide hindcast and forecast of different parameters over a period that goes roughly from early 80s to present. And they provide different ensemble size for the forecast. So that's a lot of data, and not only to analyze the scale in the seasonal forecast models, but also to investigate processes and try to explain why the models may not have a good scale, why in some years they have a good scale, in some years they don't. I think there is a lot of potential in exploiting this data to understand physical mechanisms. So a quick example for a case study of 2014-15. So this is a time series on the left of California precipitation. So that year was pretty wet and then became dry in the second half of the season. So there was a trough in October, December. That's the 200 anomalies in NCEP. This trough turned into a ridge in January, March that blocked any storm atmospheric river to reach the western US coastline. And that's the precipitation anomalies at the bottom. So we see we have negative precipitation anomalies, no rain during the second half of the season. And so we explored the NMME ensemble to see how the models did in terms of forecasting this season, and especially this transition from a trough and wet conditions to a ridge and dry conditions. So on that plot, Yuna shows Z200. So it's a measure of the ridge in the North Pacific in October, December, versus a measure of the ridge in the January-March season. So what we want here is the models to be in that section of the plot, because in observations, we had negative geopotential anomalies, a trough, and then we had positive geopotential anomalies, a ridge. So we see that only a handful of forecasts are able to represent that shift. So then in the next slide, I compare the forecast, what we call the good forecast, the one that are in that quarter of the plot, with the poor forecast, the forecast in that section. On the top, this is the 200 anomalies in October to December. For the good forecast, the poor forecast, the number of forecasts is given in parentheses, and then the difference between them. And this is for January to March, at the bottom. What's striking during this year is that the poor forecast, they kept some sort of a zonal circulation regime throughout the water year season, while in the good forecast, there is a wave 4, wave 5 type of pattern emerging that we also observe in observations. And that's even more striking when we compute the difference between the two. So this is very preliminary, but we are trying to understand what may be the cause for this difference in the large-scale circulation signal between good and poor forecast. And if we can identify drivers that may explain the differences between good and poor forecast. Yuna has some preliminary results on this, and she found that there is an effect of the mean state of the model. So on that plot, this is a bias of U200 in the North Pacific. So basically the bias of the North Pacific jet in the mid-latitude in the North Pacific versus the Z200 anomalies in the North Pacific. So the good models should have positive anomalies because in January there was a ridge in observations. And what she finds is that the forecast and models that have a smaller bias in the North Pacific circulation have a better representation of the ridge anomaly. So they seem to do a better job in predicting the ridge for that specific January month of 2015. So now we want to explore this further and try to generalize it with more models to see if that result is really robust. So I'm at the end of my presentation. Some quick conclusions. Are water area, California rainfall, and regime shift in this rainfall predictable? So we've seen that in WACAM, the potential predictability associated with global SST is limited to ENSO years. And the AMIP runs, when we prescribe global SST, do not capture regime shift in California rainfall. However, if we nudge the tropical troposphere in the model, and especially prescribe the MJO, we see that we get a better representation of the North Pacific circulation anomalies and of the regime shift years. So really, it does not mean that we can make any prediction using the nudging, but it means that if we were able to improve forecasting in the tropics, that will increase the scale in California rainfall, and that will be beneficial to seasonal forecasting of California rainfall, especially for the regime shift years. And then I've shown that despite the dramatic changes in the last decades, narrative variability does not seem to play a role in California rainfall, interannual, and multi-year variability in our model. Future work, we want to further explore those simulations to investigate mechanisms and the regime shift years, especially. We may run additional simulations with no QBO. So QBO is a quasi-biennial oscillation. This oscillation is a stratospheric equatorial winds. That is another source of seasonal predictability. I didn't mention it, but it's prescribed in our simulations because WACAM has an option to prescribe the QBO. So if we remove the QBO from the AMIP simulations, it may be interesting to see if it affects the results, especially because we know there is a connection between the MJO and the QBO. So that would be a way to investigate the MJO-QBO teleconnections. We want to do more systematic analysis of the North America multimodal ensemble to dig further and see if we can understand what differentiate good versus poor forecast for the regime shift years, especially. And then I didn't have time to present any results on that component, but we are working closely with Eric and Gabe from the Department of Computer Sciences on developing statistical models to predict California rainfall at seasonal time scales. And we hope that we can bring some expertise in the processes to help them to integrate the right drivers in their statistical models. So that's a pretty complementary work we have with them. And that's it. Thank you very much for listening.
Okay, thank you, Yannick. And we have time for questions, and especially starting with any early career scientists. If you have a question, indicate that in the group chat. You can also try raising your hand, but with this many people, I think we can't see everyone at once. So any questions?
Alex, if no one asks a question, I have a question.
Yes, please go ahead, Jinyi.
Yeah, Yannick, thank you for this very interesting study, and I'm particularly interested in your first part of the result, which I think you compare the AMI run with the AMI run not constrained by tropical observation, and you see that the simulation of California rainfall increased, become better, and I think that improvement seems to be particularly clear for the 2015 and 16 El Nino. Yeah. And I was wondering whether or not this result is dependent on the WACO model you use. So if you do not use WACO model, you use the CAM AGCM instead of WACO, do you still see the similar problem or not? And the reason I'm asking this is because in our 2017 paper, we are able to simulate that near normal rainfall in 2015-16 using a similar force AGCM run, but with the CAM model. Yeah, that's the reason I'm asking.
So I don't see any signal in the stratosphere for that specific year. So I assume that if we were using CAM, we would get pretty much the same response because there is no really role of the stratosphere. The benefit of having WACAM is to have a better result stratosphere, but maybe the QBO may play a role. So that could be a factor that if you use CAM, you don't have the QBO. But yeah, that would be really interesting to check. Thank you for the comment.
Yeah, thank you.
Any other questions? Maybe just following up on that, Yannick. So what? Why are you using WACAM? What do you expect? What benefits do you expect to get from having the upper atmosphere?
So like I said, there is the option to have the QBO in WACAM, and we know that's a source of predictability at seasonal internal timescales. So that's really interesting for the QBO. I'm not sure it plays a role for that specific 2015-16 years, but it's interesting for us to have it included in our simulation. And also for the high latitude simulation, we know that the stratosphere play a big role in extratropical variability in winter. So it's really important to have the stratosphere, especially for the AMIP high latitude simulation. So there may be a stratospheric response to the forcing we impose in the troposphere.
Yannick, could I ask the other question related to MJO? So when you constrain the AMI run with the relaxation, you're including all the frequency in your observation, the one you try to constrain. So you come to a conclusion that MJO in a tropical region is important to improve simulation of California rainfall, or is important for California rainfall. So if you repeat that experiment again, but you filter out the MJO signal, 30, 50 day in your constraint variable. So you constrain everything except the 30, 50 day band in that prescribed field.
Yeah.
Are you able to get the similar rainfall in California?
Yeah, I don't know. That would be really interesting. I'm not sure we could nudge the model with a filtered field like this, because it would be quite unrealistic. We would miss some high frequency variability in the tropics. So I'm not sure how the model will react to that. Maybe it's possible actually, because we are superimposing the anomalies on top of the model climatology. So we may filter the anomalies only and not the climatology. So yeah, that could be something we try. It would be really interesting.
Okay, thank
you. Okay, well, thank you, Yannick. I don't see any other questions, and so I think we'll conclude and virtually thank you for this outstanding presentation.
Thank you very much.